Thank you. So our final talk of this session is from Adam Trapp. So Adam, if you want to get your slides up.
Sure, thank you. Let me make sure this is the right one. Can you see this?
Yeah.
Awesome.
Right,
great. Well, awesome. Hi, everyone. My name is Adam Trapp. I'm a fifth-year PhD student at UCLA. And first, I want to say thank you to the organizers and for the opportunity to give a talk at SAZERAC today. Okay, so I'm going to be talking about a framework for simultaneously measuring large-scale environments and the galaxy luminosity function. And this is work that I've been doing with Stephen Ferlinetto at UCLA. So I don't really need to explain to you all why we care about the UV luminosity function. We've had some great talks today and throughout the conference. It reflects the growth of galaxies over cosmic time, and of course, JWST will measure the luminosity function at much earlier times and with greater accuracy than currently possible. But my talk title also mentioned environments, and so why do we care about measuring large-scale survey environments and densities? Well, some of the other speakers kind of got ahead of me on this, and I'm going to give my own take on why these are important. But first, let's talk about the effects of environments on the luminosity function. So survey environments differ because of large-scale fluctuations in the underlying dark matter density field, as many of you know. An overdense volume will have more galaxies than average, and underdense will have fewer, and this effect's called sample variance or cosmic variance. And cosmic variance can be estimated via galaxy bias factor, which I'm going to call epsilon CV for this talk, which represents a 1 sigma deviation from the average luminosity function, and it can be estimated via theory, as we did last year, or it can be in simulations, as many people have done. And in short, a survey's environment can change the normalization and shape of its own local luminosity function. So let's take an example here. For a 100 square arc minute survey, cosmic variance always dominates Poisson or shot noise at the faint end. That's these red curves. The solid is sample variance, cosmic variance versus the Poisson variance here in the dashed. And it can dominate at the intermediate and bright end up to pretty high redshift. These are the different areas. If you want to see the effects of cosmic variance on your survey volumes, I have a handy Python package for you, and there are others out there as well. So how do we deal with this cosmic variance? In current works, cosmic variance is corrected for by fitting the shape of the luminosity function across fields, and then at the end you normalize. And this method works well, but it has some drawbacks. First, the normalization of an individual field is ignored, so we can't leverage our knowledge of galaxy bias during the fitting, and we lose potentially useful information about the environments. And the second thing is at higher redshift, cosmic variance affects the shape of the luminosity function more than at lower redshift. And by higher, I mean greater than 6, the areas that JWST will be probing. So this method can't address that. So our framework fits the luminosity function and each field's density simultaneously. Basically, we give each field its own conditional luminosity function, and what that means is it's the average luminosity function times a factor which has to do with the galaxy bias function, which I mentioned earlier, and then this n value, which is the free parameter for each field. It's not really free, it has a normal function prior. It's the number of sigmas off normal, you could say. So for example, if we fit the Finkelstein data from 2015 using this method to compare, let's see here, we get similar constraints on the Schechter parameters at redshift 6. And then this isn't the most recent luminosity function measurement, as we've heard, but this is the most recent one that I've gotten to reproducing so far. So we recover the same constraints on the Schechter parameters at redshift 6 and also at the other redshifts. So why am I giving this talk about this new framework if we get the same answer? Well, our method's main benefit is we get the posteriors on the dark matter densities of all the fields, right? So this is the posterior space. For example, the Goods North field, using our posteriors, they say that the Goods North field is about 1 bias factor underdense, and the Hubble Ultra Deep field is about 1 bias factor overdense. this is the n value, right? So the actual overdensities depend on what that epsilon CV parameter. It can be between 10 and 40%, depending on the location on the luminosity function, because this galaxy bias is a function of luminosity. And I want to mention that I've added Bowler 2015 data here because it helps with the bright end and with the normalization. Okay, so we have these n values. So let's go back to the question that I asked at the beginning is why do we care about the large scale densities? I probably don't need this slide considering all the talks we've had about how important densities are, but I'll go over this. So the density provides info on the past and future of a region, whether it'll become a protocluster, its reionization history, etc. And it also allows us to check, if we know what these densities are, so we can check for environmental factors in galaxy evolution, like differences in the star formation histories between an overdense region and underdense region. Also, as we've heard talks about, finding overdensities can assist in locating Lyman alpha emitters that are inside the earliest ionized bubbles. High redshift galaxy formation is strongly affected by large-scale radiation backgrounds, which will be determined by the large-scale density fields. For example, reionization will suppress the formation of small galaxies through photoheating, and identifying environments helps us understand these radiation fields and their feedbacks and their effects on the different parts of the luminosity function in the galaxy population. And finally, this isn't an exhaustive list, but measuring survey environments provides a quantitative check on our understanding of galaxy clustering in the first place. All right. So an obvious downside to this is now we have to fit for many more parameters, right? There's an n value that we have to fit for simultaneously for each one of the fields that we have. And that can be a lot of fields, but fortunately, the fields environments are independent of one another. And also, crucially, we can combine multiple fields into a single survey with an effective galaxy bias function and a single n value to reduce the number of parameters. So for example, if you have a parallel program with 150 independent pointings called panoramic, we can combine those all into one effective survey, one survey with an effective galaxy bias function in a single environment. Okay. So I've been talking about using this method on current data, but we can also use this framework to predict how well JWST programs will measure the luminosity function and simultaneously the environments of the individual fields. So I've taken a couple programs that we've all heard talks about this week. Some are mosaic, some are parallel, and we make a very simple simulation of these surveys at redshift 6 to 12, drawing from the luminosity function in Finkelstein 2015 as the truth, and then we assign these fields random environments. Then we use our framework to fit the simulated data and obtain posteriors on the Schechter parameters and the environments, and then we compare the different surveys. And I want to give it another highlight the fact that this is a very simple simulation, and the goal here is to get an idea how well these various surveys will combine and complement each other to measure the UV luminosity function and the large-scale environments. And so on this plot, I'm showing basically, if you want to get the environment of a single volume, getting other volumes helps you in your knowledge of that first volume. So that can be shown here. So on this y-axis is the width of the posterior in determining the density, right? And so for example, if you wanted to figure out what the density of the Jades North environment is and you do the Sears survey and the Jades survey, you can get some constraints on what the environment is of the Jades North environment. But if you add primer, you get a better determination of the Jades North environment. And if you add panoramic, you do even better. Right. And so this is the reason that getting different sources is getting you more information on the first sources, because you're fitting these all simultaneously and they help each other. Though you might notice that you're kind of getting diminishing returns, especially up at high redshift, and that's because once Poisson noise becomes about the same size as the density, the change in density of your posterior here, you can't do much better. So there's sort of a Poisson noise floor to determining densities. And this is just one example. You can also do this, here's the same thing, but for the Sears environment, and you could do this for all the different environments in any of these surveys that you're simultaneously measuring. And I also want to add that I'll be adding Cosmos Web and WDeep and Uncover soon to these analyses. I think Cosmos Web is especially going to be helpful because it's really going to get the faint end, or sorry, the bright end with the large volume. And from there, I'm just going to say thank you for listening, and I'll take any questions.
Thank you very much, Adam. So we'll just wait a few seconds for the questions to come in on Slack. Actually, while people are thinking, I might take an opportunity to ask a question myself. Just on your last slide, for these measurements of the overdensity, can you explain to me what the error bars in those plots are coming from? Because I guess I would expect if you just use one survey, you should have they should be consistent with each other within large error bars.
Exactly. So if you just did this once, you make one set of fake data and you do the analysis, you get a really jagged line here. So because the densities can be different and you can get different Poisson noise. So what I've done is done this multiple times. So I think this is between 5 and 20 times, and you get, this is showing the average, the sort of the average posterior widths that you'd get. Does that make sense?
Yeah, I think so.
Yeah, it's like because the width is going to be some value if you just run it once, but if you run it multiple times, you'll get sometimes you'll do better at measuring the environment, sometimes you'll do worse.
But I guess my question is that maybe they're biased, or so, because these are all had the same input.
Each time we run it, we give it a different random seed. And so, for example, in one, maybe the Sears environment is 2 sigma overdense, and the next time we run it, it's 2 sigma underdense. And so, because we want to, maybe we got a really bad draw on the random numbers of the environments between the different runs, if that makes sense.
Okay, thanks.
So this is sort of showing you the intrinsic variation in how well you can do. Sometimes you will do much worse, and sometimes you will do much better, depending on just what the random environments and the Poisson noise gives you.
All right, so we got the first question from the Julia Munoz. So do you expect to get enough density measurements to be able to correlate them and learn some cosmology too?
Correlate them and learn some cosmology too. I'm assuming you're meaning sort of you get enough density measurements to sort of re-inform what you know about galaxy clustering, and if that's the case, if not, you can clarify your question and I'll answer it. But yeah, that would be great. That was, I guess, one of my points is that you can do these measurements and you get the measurements of all these different environments, and then you can check and see if that's consistent with our understanding of how halos cluster and how galaxies inhabit halos.
Okay, there's a question from Naku Gangoli, and he asks, I may have missed this, but how did you determine epsilon CV, and would it depend on environmental factors?
Yeah, so epsilon CV is the galaxy bias function. It's the it's been done theoretically for a long time, and we just recently came up with a paper giving our updated version of how you would calculate this galaxy bias function. So I can refer you to my paper, and I can also talk to you more about it perhaps in the Wonder Me session if you'd like to come. But it's as for its environmental factors, it depends on the redshift of the survey, the size of the survey, the shape of the survey, and of course the luminosity that you're looking at on the luminosity function.
All right. So then the question from Rick Mentor. So I'm a bit confused. So using multiple fields, allows you to better estimate n for any one field. Is that because you assume n goes to unity with a very large set of fields? In other words, you've sampled enough that cosmic variance isn't relevant?
Yes, that's a great question. So maybe I'll give a little mini thought experiment here. If you take one measurement of, say, one survey and you get really good data, you don't know what this n value is, right? Because you're trying, it's degenerate with the phi value of the average luminosity function. So by simultaneously fitting the average luminosity function, you don't know what n is at all if you just have one survey. But if you take a second survey or multiple other surveys, basically those multiple other surveys are sort of doing the work and figuring out what the actual intrinsic normalization of the luminosity function is. And then so for the first survey, you can say, well, this first survey has fewer numbers than the average, and so it must have a lower n value. It's not exactly how it works. It's all done simultaneously in the posterior fitting or the posterior generation. But basically, the other surveys acts as a sort of lever to tell you that this survey is underdense or overdense. And the more other surveys you have, the better you can do for that first one.
Okay. Thanks very much, Adam. And thank you very much to all of our speakers in the session today.